Welcome to the sixth lecture. Today is the first day that we can actually use all these basic ingredients that we covered in the first third of the class, and we can really do some cool stuff. Also, you have sort of the most basic models now in your repository, but in order to really get them to work, you don't want to make some very basic mistakes. So the first thing we'll do, now that we know sort of the basic math, the basic model types, is really understand how to use them properly. And there will be some things in here where if you, for instance, initialize your weights incorrectly, nothing will happen and the models will be terrible. So some of these tips and tricks here are incredibly important, and you do really want to know them to make the most of these methods. And so once you know a couple of these tips and tricks, we can go to the really first sophisticated model of the class, which is a recurrent neural network. It's a very powerful model. It can solve a lot of different tasks in natural language processing. It'll be sort of more advanced but still basic building block for other more complex systems in the last third of the class. Are there any questions so far about organization? The problem set is due tomorrow, so please submit. You have at most 3 late days, which unfortunately then I guess will be Sunday, which will make it hard to submit. So make sure you submit it on time. All right, so there'll be a bunch of different tips and tricks, and then before we talk about the recurrent neural network models, we'll also cover language models. It turns out one of the earliest usages or usage of recurrent neural networks was the task of language modeling, which is not to be confused with modeling language, which is what we do in general in this class, but actually just predicting the next word and predicting sort of sequences, or assigning probabilities to various sequences. It's a very fundamental and important task in NLP, and we'll cover it a little bit. All right, so let's start with some interesting techniques. The first one is really a special type of model, but it's also one that will sort of trick that will allow us to make use of various different models and get the performance, improved performance. Basically, it's called multitask learning. And you could also just say we're sharing weights between different tasks. We've already shared weights in word vectors. Word vectors we initialized with one model, and then we had our window models trained to do something else, right? And we will actually just continue doing that across different layers of the neural network. So our base model is exactly the same single hidden layer neural network from the last class. But instead of using a single scalar score, we'll just have our standard softmax classifier. So just so we're all on board here, so this is basically our standard definition, again, of this single layer neural network model. And this is, again, just a toy example. Of course, in real life, our word vectors might be 100-dimensional. And we'll have 5 of them, so we'll have a 500-dimensional input, and we may have like a 100-dimensional hidden layer, and then 5 classes or so. So here we just have a very toy example just to illustrate the model. Training is, again, just done via backpropagation, which we now hopefully are all familiar with, and is just taking derivatives with respect to our loss function. This model here actually has been shown to be quite successful on a couple of different NLP tasks, and we'll go over some performance metrics at the end of this subsection. And this was a paper that I encourage you all to read. I think we link it on the website too. It's called NLP, or Natural Language Processing, Almost from Scratch. It's by Ronan Colobert, and the original paper by Ronan Colobert and Jason Weston. Jason Weston will actually also give a guest lecture later in the quarter, and then Ronan and many others sort of extended it in a journal version, and have this paper here in 2011 that kind of cleans up the original submission at ICML 2008. So basically, we already know our softmax classifier and how to optimize it. And the main difference here of standard machine learning and deep learning was that we also have now an actual training step for the input word vectors and the hidden layer. And we already had shared the word vectors between different models. So this should be nothing new, right? And we can have different types of scoring functions here, softmax or the inner product. The main idea of multitask learning now, and this is a general idea, but I'll illustrate it here with this kind of model, is that we can not just share the word vectors, but also the hidden layer weights across multiple different tasks. And if those tasks are actually related, it might actually help and improve performance to do that. So in this case here, only the softmax weights are different. Everything else is shared between different tasks. So our cost function in this case would just be the sum of two cross-entropy errors, summed over all the different training examples for both of those different tasks. So, you know, basically here, this is the formulation of a single layer neural network. And now the only thing that's different is we have two different W's for one softmax that classifies these three classes and another softmax that classifies these three classes. And so if you were to implement this, or well, let's give you an example first and then we'll talk about implementation. So one example would be, again, our standard named entity recognition that we're now getting all very familiar with. We can classify the center word of a window as, you know, location, a person or an organization, or none of the above. And another task that is also a very simple word classification task, and the two are somewhat related, is part of speech tagging, or in short POS tagging. It's not very complex. You basically assign every word in your language a part of speech tag. You have determiners, for instance, like a and the and this. You have nouns, which are, you know, abbreviated as n. You have proper nouns, n and p, and proper nouns like, you know, Richard or Ethiopia or and so on. You can see are very related to named entities, right? Most named entities probably also have to have an n and p here as their part of speech tag that is assigned to each word. You also have tags for adjectives or superlative adjectives and various different sort of classes, also of noun phrases and or nouns and plural nouns and so on, and verbs and so on. So basically, every single word has a tag that linguists assign to that word, and they group them. So now, the simplest thing you could do is just you do forward propagation, you compute your hidden activation here, A1 and A2, and then you predict your part of speech tags, and then you just do that, you train it, and you're done with it, and then you take those weights and you train it on something else. But that wouldn't be very efficient, and now you might also, with the second classification, mess up the first one. So what you'd rather want to do instead is actually combine and train both of them at the same time. And there you could basically now go through each window. Let's say you have one corpus, and every single word in that corpus has both a named entity tag and a part of speech tag. Now you could go through that corpus, and for each window say, first I'll do forward propagation, then I know what my cross-entropy error is for part of speech tags. I propagate that through the model, take derivatives, make my update steps with stochastic gradient descent, and then use that same window, do forward propagation, compute my cross-entropy error now for the other tasks, and then basically propagate into that. That's possible, and that's certainly, you know, a correct implementation, and that will allow the model now to basically solve both of these tasks at the same time. But it's not very efficient, right? What you could instead do is you actually, the first part, constructing your window, which you're, probably have, most of you have done by now for problem set 1, you construct your window, and then you multiply the matrix W here, and you add your bias term, and then you add your element-wise you apply the element-wise nonlinearity here to the resulting vector. Both of those models have the exact same steps in here. So why not just do it once, and then keep around your hidden vector, and then just apply two different softmax weights to that, or multiply your softmax matrices to the same hidden vector. And then when you actually do the math, you'll realize that your error messages, delta, that you get from a softmax, which was usually your target minus your prediction, will actually just sum up. So you can now take your delta from this softmax, add it to this delta of this softmax, and then you actually can do have a combined update for the lower layer as well. Are there any questions about that? Yes?
If you're interested in just one of the two tasks, does adding the other tasks allow for better generalization on the other one, or is there evidence of that you can actually apply multitask learning just to improve your model generally?
That's a great question. So let's say you really don't care about part-of-speech tagging, but you just really want to have accurate NER. In that case, it can still help actually, if the tasks are related, to train both. But in that case, if you really don't care about the first one, you might just want to first train that, just like we sort of separate out the word vector learning from the final task learning. You train first your word vectors, then you train on part-of-speech tagging, and then you have your weights. You initialize your weights with that instead of randomly, and then you train named entity recognition on top, and that has been shown to also improve the performance. Yeah. Yeah. That's a great question. So what if your gradients here, your delta that comes in here and here is significantly larger for one? In general, that shouldn't be the case if you use two kinds of, or the same type of cost function for both. But you may eventually also combine a max margin cost function here that gives you a specific delta and add a delta from some softmax. So in that case, that could actually happen, that your deltas come in at different sizes. And so what you want to do as you implement this is ideally in the first iteration, when you first start out, you visualize your weights and you print out their magnitude. And then you can basically say, all right, this is always larger than another one, so maybe I should initialize the weights differently, such that, you know, for the scoring function, for instance, that wouldn't be the case. You might want to regularize the different weights differently. So far we've talked only about regularizing the entire vector theta of all the parameters with the same regularization weight, but maybe you want to actually have different subweights. And then the last one is you could just have a weighted sum of your cross-entropy errors here. So you basically have cross-entropy error of this plus alpha times cross-entropy error for that classification problem, and then your alpha could just be 0.1 or something to lower the weight of the other. All right. So this kind of concept here of adding deltas will come up again and again. So if this doesn't make sense, it'll be good for you to actually really write out in your notes two cross-entropy errors, really in detail take the derivatives of both the same way we've done it before, derivative of, you know, the sum of two things where the same things inside is just the sum of the two derivatives, and then you can basically go through that and see that these are really the same. Yes?
So for the last layer, the softmax layer, we only updated with just one task separate?
Yes, that is correct. So the first, right. So the first delta here, yeah, that's a great question. So we of course don't want to take the very first delta. Okay, this is a really good question, and I'm worried nobody else had asked it before. So basically, what I wrote here is the deltas, that will only be true for the things that are actually shared. Right? It will not be true for the first layer of the softmax weights. So the very first delta is indeed different for this classification problem and this classification problem. But then once you go to the layers that are actually shared, then those deltas are the ones that you sum up. Yeah, excellent question. All right, so it's really important to do this weight sharing and multitask learning, especially for the word vectors. A lot of these models, when you ask these models to learn everything that used to, you know, require a PhD student to design various features and so on, now you ask it to learn all these patterns by itself. It's really important that it sees a lot of data. And one way to have it see a lot of data is by having this unsupervised word vector pre-training. So here are some real numbers on the two different tasks we just discussed. Part-of-speech tagging on a very standard corpus called the Wall Street Journal, which was annotated very carefully by linguists a long time ago. In fact, the linguists discussed and argued so much about how to really properly annotate it. I think eventually it was classicists who did the actual annotation on a large scale. But basically, this is one of the main data sets for part-of-speech tagging. And then here's the Connell task, which was a shared sort of competition a couple of years ago, almost a decade ago now, for named entity recognition. And for part-of-speech tagging, every single word has a part-of-speech tag, so accuracy is a reasonable measurement. but as we discussed for named entity recognition, most things aren't named entities. All the adjectives, verbs, and personal pronouns and so on aren't named entities. And so we use the F1 measure here to compute how accurate systems are. The first row here is a sort of standard NLP state-of-the-art system. The two representative systems that we use here are one by Jutanova and Ando and Chang from more than a decade ago now. Part of speech tagging is really quite a solved task. We can do it really, really accurately now, and really most models can do very well in part of speech tagging. So when you have 1% improvement here, that is actually quite significant, just because like everything gets sort of like every model and their mother gets to 90 plus on this task. It's different for named entity recognition, where it's a little harder and there are bigger gaps. So a state-of-the-art sort of traditional NLP system that used tons of feature engineering, had a couple of grad students. In fact, Tutanova was one of Chris Manning's grad students back in the day. Lots of feature engineering to really try to solve these tasks accurately. Now, if you just take your neural network, you initialize your word vectors randomly, and you just train on that specific task, then you can get away with it for part of speech tagging, because it's a really simple task. Every word has a label. But for named entity recognition, you actually do quite poorly. It's 8% below state of the art. So this is basically, this shows you that if you just train on one task, and that task doesn't have a gigantic data set with lots of labeled examples, even though your neural network is this very nice, very complex model that in theory could train very interesting decision boundaries and so on for your problems, if it doesn't have enough data, it doesn't do well. Now, if we take our word vectors and we actually take these pre-trained word vectors and we initialize all the windows and all the word vectors with those for this task, then we actually start doing a lot better. So here we have almost 1% for part of speech tagging, an increase, and over 7% for named entity recognition. So this basically shows you that the word vectors themselves actually do capture a lot of information about syntactic and semantic content of each of the words. Yes?
Did you work on multitask learning between different fields like NLP and vision, machine vision?
That's a great question. Has there been sort of multitask learning between completely different modalities or fields? Yes and no. So in many cases when you do that, you don't really call it multitask learning. It's very hard to say I have an apple here, images of an apple, and I have apple in the text, and now I want to learn more about the apple by training on strawberries and so on. So what has been done is actually a very interesting paper. Well, okay, I don't want to. A paper I published a couple of years ago that allows us to do zero-shot learning when we combine different modalities. Don't worry if you don't fully follow what I'm about to say. I'm just going to describe this NIPS paper from 2 years ago really quickly. Basically, the idea is you have these word vectors, and you have word vectors for a bunch of different classes. Let's say 100 different classes, and now you have images that are actually showing a subset of those word vectors in the actual thing. So let's say I have truck, and actually maybe I can. All right. It's usually a bad idea to do something live, but it's a great question and it's a fun answer. Sorry, where's my mouse? Zero-shot learning through cross-modal transfer. So here's the idea in a toy visualization. So basically, you have a bunch of word vectors. These are the ones that have boxes around them. And now you actually train, turns out, also a neural network that maps certain images for some of those classes to be very close to those word vectors. You just train a neural network that should predict as its output a word vector, essentially. And so you take a bunch of little images and you try to map them to be close to their word vector. So here we have a bunch of horse images, a bunch of car images and a bunch of dog images, and we try to have all these images, no matter what the dog looks like, we try to eventually train a neural network transformation such that the output of that neural network gets to be close to that word vector. And we don't update the word vectors. They're just from what you've learned before with GloVe or Word2Vec kinds of models. And now we have some word vectors here for which we've never seen a single image. And then you can actually take an image and you map it through that same neural network you learned on the other things you have seen before. And then you ask, okay, is this resulting vector of the image close to any of the classes that I've seen before? And if it's not, then I can just fall back and see, well, is it close to one of the word vectors that I haven't seen before in my visual training data set? And then it turns out you can actually assign images with the right class without ever having seen an instance of that class. And it's kind of crazy that that works at all. And of course, they're only in certain cases when it works. If you take out dog and cat and there's nothing like it that it's ever seen in a visual world, you won't be able to do as well. But if you've seen cars, horses, and dogs, then you get very good and over 90% accurate at distinguishing cat and truck images, for instance, just because they're quite separate and in the both in the word vector space and then in the visual space. So that is sort of a long answer to you can do multitask learning with these word vectors, but it's not quite multitask learning, sort of just multimodality learning. All right, so we basically have here our word vectors, and now we do pretty well on this classification problem. And now this is sort of an unpleasant line if you're a hardcore deep learning person, in the sense that this is adding handcrafted features to the original system. And this is of course something that we'd like to avoid. But if you really want to squeeze out that last extra bit of performance and have now a state-of-the-art system that is, after the dot, a little more accurate than the state-of-the-art, then you can do that. And we'll actually, maybe in a later lecture, describe how to actually add handcrafted features to these models. But what's more interesting is basically you can also fix your embeddings and you can backpropagate your actual signal into the word vectors too. So what do I mean by this? Basically, you can assume your word vectors come from the Word2Vec model that you've implemented in pset1, and you just add them there, and then you don't take derivatives with respect to those word vectors. You only update your weights of the softmax on the hidden layer. Or you actually take the derivatives with respect to word vectors and update those as well in your stochastic gradient descent. And so if you do that, it turns out to help a little bit. And with that, basically you can get to a system that's even more accurate. And those are two very sort of fought over tasks in the academic community. And so being able to improve on that is quite exciting. All right, so that was multitask learning. Are there any other questions about multitask learning? All right, so let's look at some general strategies for successfully training neural nets. This is some of these are very important, and you do want to pay attention to some of these steps, because you could really not do well at all, no matter what you do, if you mess up some of these. So here are the couple of steps, and we'll walk through all of these now carefully. The first one is basically just selecting your network structure appropriately for your problem. Do you care about single words in the context of a window? Do you really need to look at the entire sentence, or for instance tweet, in order to make a specific decision? Do you want to look at the entire document, which is something that is harder and actually hasn't, deep learning doesn't always succeed as well here as on some other tasks. Do you care about your word order or not? So this is sort of a different set. Which kinds of models based on your input structure do you want to then use? And most of those we haven't discussed yet, convolutional neural networks, recursive ones, but recurrent ones we'll get to later today. And then once you have your general structure, one important hyperparameter is which kind of nonlinearity you use. And this will come up again and again. And so we'll go over a couple of examples in the next slides. And then there will be lots of ways of making this work and sort of helping you get unstuck as you develop and implement your own neural networks from scratch, where maybe you won't have a p-set that sort of gives you starter code in the future. So, nonlinearities. We started out at the very beginning by motivating neural nets as sort of little logistic regression units, where each unit is on with a certain probability. It turns out that is actually not necessary. So, you can have your activations, your nonlinearities, be the logistic or sigmoid function that is between 0 and 1, but you can just as well use the so-called hyperbolic 10 or 10H unit that basically maps values to be between -1 and 1. One thing that's important for any nonlinearity you want to try is that you want to ideally be able to compute its derivative by using only the actual function value itself. So f of z is something that we compute during forward propagation. Now, if during back propagation you need to run another exponent, that would be quite expensive as you do it, millions of times. So the great thing about both the logistic or sigmoid and the 10H is that their derivatives can be computed in terms of just the actual function value. So it'll be very efficient to do that. You could actually argue that 10H, doesn't really matter because, mathematically, you just can rescale and shift a sigmoid to get exactly a 10H. So it's just, if you multiply all the input weights, for instance, or your inputs, the inputs themselves by 2, and then you apply your sigmoid, and then you multiply that output by 2 and subtract 1, you actually get the 10H unit. However, as you stack these layers multiple times, for many models, 10H is, gives you the best performance. It's nice because at the initialization, if you have a bunch of little random inputs that are either normally distributed or have a mean of 0, it's nice because all your subsequent layers will also be close to 0. And that way, as you sum them up multiple times in a row, they don't max out and they don't end up as quickly in sort of the so-called saturated area of your nonlinearity. And we'll get to that, the intuition of the saturation of a hidden unit in a couple of slides. But basically, it's just a unit is called saturated if its input is very large, such that you then end up in this sort of very flat regime of your nonlinearity. 10H does, in practice, just gives faster convergence than the sigmoid. And again, has also a nice derivative. All right, those aren't the only ones. This is obviously an important piece of the whole neural network puzzle. So a lot of people have tried a lot of different submethods, and not all of them are super principled. Sometimes there's certain intuitions. So the hard 10H is basically just a very simple linear function that then is basically saturates entirely and for most intents, will not allow any gradients to come through once it's saturated here. Right? The gradient of 1 will just be 0 no matter what the input is, as long as the input is larger than 1 here. So this one is very, very efficient, right? You basically just have to return x or kill x. So it's a pretty efficient way of doing it, but it doesn't have the nicest properties. One thing, nonlinearity that was sort of popular for a little bit, but not for very long, was the soft sign. And here, the intuition is the soft sign has sort of a nicer linear sort of area. It doesn't saturate as quickly. Basically, you want to often avoid saturation, especially if the saturation is very high, because then that unit cannot learn anything anymore for subsequent layers, or you can't update it anymore with new data. This one is really the most popular one right now, and for most computer vision models, this is the default nonlinearity, and it's also very fast to compute and very, very simple. It's basically just any input that comes in that is smaller. All right. So, parameter initialization. So why is this so important? Let's go through an exercise and see if you already have this intuition. Basically, let's say we have our nonlinearity, And let's say it's the tan h, which is a great nonlinearity. And now let's say, so this is basically, in order to compute this, right, your x value here, or usually we call it z, this is just 1 wi, the ith row times your input x. And then we get here f of z. Now, let's say we want to compute our derivatives for f of z, and let's say we initialized our weights w here. Let's say x are roughly between -1, all the x elements here, so each xj is roughly between -1 and 1 from our word vectors. We can make our word vectors, we can pre-process them, for instance, to be like that. So now, let's say we initialize our w elements of the first hidden layer to be between -100 and 100. Right? It's terrible, and you wouldn't want to do it, but let's say we did that. Now, what happens to our z if, for instance, x happens to only, have one element that is 1 and one of those that is 100, and everything else was 0, just for sake of the argument. It's not usually what word vectors will look like, but let's say our z here is roughly 100, and we end up in this part of our nonlinearity. What will happen to the derivative? What does the derivative look like in that case? Exactly, it's 0. So if I initialize all my weights such that all my units are close to 1, if this was the tan h, then, and I want to now make update steps, so maybe, I have here my theta, my j of theta, and here I have my theta. Basically, I initialize my model, and this is what my objective function will look like. The model has no idea where to go in order to actually optimize anything. And so you initialize your model badly, nothing will happen. Your gradient will just, you can plot your cost function, and these are all good plots to make. So here you look at your cost, j of theta, you initialize it, and it'll just basically look like that. Nothing will happen, and you're screwed, and you're like, deep learning doesn't work, and you move on. Go back to SVMs. Right? And this is actually, it's kind of funny, but this is some people made those mistakes and then said, oh, neural networks don't work, right? Like, I tried it, and they fail miserably. And of course, they fail. So what you really want to do is you want to initialize your weights w here. You make some assumptions based on your statistics on your inputs. And you want to initialize your weights w such that you start out in the beginning of your optimization somewhere in this nice linear regime here of your nonlinearity, where the gradients actually get you to go into the right direction and then allow the hidden units to actually update. And it turns out that for 10H units, for instance, if you want to exactly end up in this space and you assume your inputs have a certain distribution, that your weights should ideally be initialized to be uniform random numbers between minus r and r, where r is essentially inversely proportional to the fan-in, which is the previous layer size. So in our case, on the windows, you have like 500. And if you have, 100-dimensional output, then this is 100 to fan out, the next layer size. Sorry, the next layer size being like, the layer above the current one that you initialize. So let's say you have, this hidden layer has 500 input, and the next layer is 100, so then you have here 600. And if you initialize, okay. If you initialize your weights that way, you should have good learning dynamics in the beginning. It's random.
That's really weird. instead.
Yeah, let's give it a try. I wonder if the light's gone out on the main projector. Yeah. So much excitement in the room that the projector died. Overheated. All right. Thanks. Thanks, Ian. All right, so that was parameter initialization. Does that make sense? All right, great. So, stochastic gradient descent. We basically talked about this already, but some people might say, well, if I really want to get the optimum update step for my entire data set, I should do full gradient descent, which computes the gradient over all the examples in my data set. And that really is an absolutely terrible idea for all realistically large data sets. It'll take you forever to compute one gradient. All the computation you do will not be as useful as if you made first a couple of little update steps, and then the next computations of forward and backward propagation will already be more useful. So also, in general, we have very non-convex decision boundaries, and I guess now is it possible to pull the other one up, Ian? GA double projector. Awesome. Great, thanks. Generally, our objective function, the j theta, if it is usually multidimensional and we can't really visualize hundred dimensional spaces, but in general, your j of theta, as you look for every single theta I of sorts, will look very non-convex like this. So if you have your full batch and that landscape, that energy landscape, or landscape of your objective function doesn't really change. And so even if you were able to do it because you had insanely fast computers, what you would do is you'd start at some random spot, maybe right here, and then you would basically make a bunch of update steps, and then you end up in this local optimum. But maybe back here, you would have had a better optimum. So those are two intuitions of why it's bad to do full batch, sort of the entire data set, and then do an update step. So we always use SGD here. So again, here JT is just the loss function at our current example T. For instance, in the window case, just a specific window that you have. And you have here your global learning rate alpha. Don't worry if you don't really know LBFGS and conjugate gradients. If you took convex optimization, then you have a little bit better idea here now. Basically, for really large data sets, SGD, or what we'll talk about in the next slide, mini batch SGD usually wins over all the other batch methods. For smaller data sets, we can use the limited memory version of BFGS and conjugate gradient. So if we just take one update step, we can really nicely parallelize a lot of computation because we have one window only. But as I discussed in a previous lecture, if we actually took all our windows and we stacked them up in one large matrix, then we can have a very large efficient matrix multiplication. This is, I basically had a little Python snippet of code where I showed the difference between having 5,000 windows in one matrix multiplication versus taking every single window in a for loop. Now, this is one of the reasons why mini-batched stochastic gradient descent actually works even better. Basically, you can have a mini-batch. They're usually between 20 to 1,000 dimensional, and we'll kind of just abuse the notation here a little bit of for J, and have basically here 20 data points, or up to 1,000 data points, for which we compute our gradients, and then we make an update step after computing those. And that helps a lot with parallelizing. Eventually, each each data point might not just be a single window, but it might actually be a complex sentence, and we have some tree-structured neural network on top of it, and it would be much harder to parallelize that easily. Once we have a mini batch, we can just take as many cores as we have, and each CPU core can compute the gradient for one of our data points. We just sum them up and divide by the total, or just average them. So mini batch SGD is sort of our default choice for a lot of optimization. One note on learning rates. Basically, and learning rate here being our alpha. The simplest one is to really just keep it fixed and have use the exact same one for all the parameters. However, that can be tuned also, and this is an important tuning parameter that can help you get better. One thing that Ronan Colobert uses, he scales them by the inverse of the square root of the fan-in. Again, just how many units are connected in the layer below to each neuron. Another one that is very helpful is to actually over time change your learning rate. So in the beginning, you let your model jump around a lot and make larger update steps in the generally right direction. But what you often observe is if this is your J theta, just your cost function, then as you train, this is just time steps now. Over time, it goes down, and then it kind of flattens out. And you should really visualize these as much as you can. Sometimes you think you can get away with just looking at a table, but it's really, really useful to look at a plot instead of a table, even though they're kind of the same information. So as the optimization progresses, at some point you basically get stuck. Now, for very large models, it can help a lot to actually now reduce your learning rate. And you often see like another drop after you reduce your learning rate alpha to, like set alpha nu to 1/10 of the previous alpha, for instance. Another really neat trick that has helped a lot for models that deal with word vectors is to use AdaGrad, which is an adaptive gradient or in general actually subgradient method. Don't worry if you don't know the difference. We don't need that for a while. Basically, the main idea here is that while SGD has a single global learning rate alpha, AdaGrad will actually allow us to have a different learning rate for every single parameter in our model. Why is this helpful? In general, when you see a word like the or a in your corpus, you've seen it so many times in almost every other window that you don't need to make a big update step to it. After just seeing 1,000 windows, for instance, you'll have a pretty good idea about the words that appear very often. And in general, we have in natural language, we have some words that we use very often and others that are used very rarely. So again, I think I brought this up before. We have, in general, a Zipfian curve where the, a, I, he, and words like this appear very, very frequently. And then it basically drops off. And then most words in our vocabulary are used very infrequently. Now, and again, all of these have a word vector associated with it, right? What you implemented in problem set 1. Now, if the words that appear all the time get a very large learning rate, and you push them around in your space a lot, they will basically jump around a lot, and the layers on top of that will have a harder time figuring out what's going on. However, for the words that you only see once, let's say you've had the capital of Azerbaijan or something, and you see that only once in your training corpus, you actually want to give it the right update step in a large direction. You don't want to have a tiny learning rate. It just barely moves away from its like random initialization, and then you never see it again. So AdaGrad will basically allow you to do exactly that. And so what does it do? So let's just define here the gradient at time step t. or it could be also window t, and let's look at the ith element of that gradient. So it's basically just what we defined here. At our current time step t, we have that gradient. Now what we'll do is we'll essentially keep a running sum for all the gradients of the past that we computed before for this. So we have one in the memory, we have one additional vector that just keeps around the squares of all the gradients that we've computed for this specific element of our theta vector before. And we basically keep summing them up. And then we take the square root of that. And then this is basically now a number. This is just a single number, right? The gradient of the ith element of our theta vector. And we have now a general global learning rate, which is divided by this gradient. So what does this do in practice for us? For instance, for a word like the that appears very frequently, this gradient will be very, very large very quickly, right? Because we see it a lot on all our different time steps. And in that case, we won't make many updates to it very soon. Like very soon into our learning and updates. However, for a word that rarely ever appeared in any of the previous time steps, we'll actually can pick a much larger global learning rate for those and make much larger updates. Yes?
So will this approach have the problem, say you have a lot of parameters, then you have to keep track the learning rate of all the parameters individually and maintain the piece rate?
That is correct. So you now have to, when your theta used to be 1,000,000 parameters in your model, which is not that hard, right? If you just have 1,000-dimensional input, 1,000-dimensional hidden layer, bam, you got 1,000,000 parameters already. You now have to keep around 2,000,000 numbers during optimization. But it's, it's just a 2x. It's not, in most cases, it's not that bad. Yeah.
So I've heard autocorrect does not work terribly well with neural networks from the vision community. Is there a qualitative difference?
That's a great question.
A year ago, so I don't know.
Sometimes these things change, but you're right. So when does autocorrect work particularly well for deep learning? It is really when you have some parameters that appear very frequently and others that don't appear very frequently. When you have a convolutional neural network, you essentially use every single parameter every single time, right? You convolve every single weight that you have in your convolutional layer and your fully connected layers. They're all basically used in every single update. So there, autocorrect won't actually give you much of an improvement. In the case of NLP, you can pick now a much larger global learning rate and make larger update steps for rare words, and that's why this kind of approach has given me like 3% accuracy or F1 improvements for some papers, and really made or helped me to actually submit this paper, because those 3% were 2% then above state of the art, and that's what made the paper. So it's for NLP, it can be really, really helpful. And there's a lot of this method, if so far you've been really bored because you are actually a convex optimization expert, go through this paper and it'll keep you busy for a while. There's a lot of beautiful math, lots of nice proofs about why this is the right thing to do, why you should really not take the absolute value here, why you have this square here, and so on. It's a lot of really nice math and motivation for it. All right, so now let's assume you were able to pick your right network structure. You implemented it correctly. You know from your finite difference gradient check for sure, without even having to ask the TAs, that it's all correct. You optimized it properly because you initialized your weights correctly to not be too large. And you made your model large enough after that to actually be able to overfit on your training data. This is an important step too. The first thing you want to do is the first thing you want to check is your model actually able to overfit and really understand at least the training data? Because if it can't even understand the training data, it's unlikely they're going to do well on the test data. But of course, we don't want to overfit in general, right? Overfitting means we do really well on our training data, but we do so well we can't generalize anymore on test data. So now it's time to regularize. A simple way to regularize is to just reduce the model size by lowering the number of units and layers and other parameters. Another really standard one is to just use L2 regularization. I actually never had that much success with L1 regularization, so all you want to do is you just add to your cost function the squares of all the elements of your theta vector. It's very straightforward, gradients are simple, and everything. One kind of hacky way to prevent overfitting is to do early stopping. Early stopping is, it's not really ideal. You basically say, before I overfit with this generally beautiful model, I just kind of stop training. And sometimes you can get away with it. In some ways it's nice in that, well, you have to spend less time training too. Like why train something that is much more powerful and well regularized but takes 10 hours versus just training something that isn't well regularized, takes only 1 hour and you're done. But of course now you have to basically all the time check whether you should stop already, so you have to evaluate on your development split and so on. Another one that is really nice and uses again the KL divergence that we've defined in one of the earlier lectures is to try to say every one of my hidden activations, this makes most sense if you have sigmoid units. You want basically the probability for this activation being on to be very, very small. So you reduce the KL divergence between some very small uniform vector that is just 0.001 in most elements and the average activations of a certain hidden unit across your whole data set or mini batch. All right, let's talk about dropout another time and actually go over in the last 10 minutes go over language models. So language models basically compute a probability for a sequence of words. So far, so straightforward. Usually you condition the probability of each word on the window of n previous words. So you want to basically know, is this sequence of words a very likely sequence? That's really the same, very simple kind of formulation. If you have a grammatical structure, a grammatical sentence of the English language, you would hope it gets a higher probability of being seen in a corpus than some random string of the English language or some ungrammatical construction. So the way we basically factorize the probability over the entire sequence is just the product of all the words in the sequence from I equals 1 to t, or in this case m. And this might seem like a rather trivial endeavor, but it is a very useful submodule for a lot of other kinds of NLP problems. So determining whether this sequence sounds more like English than another sequence is super useful for translation and speech recognition. Right? If you do a translation system, what happened until very recently in deep learning changed everything. Almost all the translation systems that are currently still in production, because the advances for deep learning are very recent, they basically first have one system that says, here's my source language. Now I create a couple of potential translations. I has cat, I have a cat, and so on. Me has cat, me have cat, and so on. It creates a bunch of different translations, and then it needs to rescore them. And how do you rescore them? Well, you look at whether that sequence is more likely or not than another sequence. And in the end, the I have a cat is probably the one that gets the highest probability out of all of them, and then you select that one to be the right translation. Similarly, with speech, there's a lot of little ambiguity, and the one that makes the most sense out of the ones that you think are reasonable speech recognition outputs is the one that is the best. So this is basically why language models are very, very useful and have been also explored in deep learning. In fact, this is an exciting model for deep learning in NLP, and so we're generally not that historical, but this is really an awesome paper from Yoshua Bengio from 2003 that in some ways is the first sort of really large-scale deep learning for NLP model. And we basically can use our standard notation here to understand this model already, and there's with one caveat, a so-called short circuit connection, or sort of skip layer. So this one here right now is the same standard 2-layer neural network that we've defined so many times now. And this is the original picture from the paper. And so I think you're now basically able to read this paper even without me. But let's basically look at this one extra notion here, which is this skip layer. So basically here, this is just a different notation for having word vectors. Here he calls them C. And you have a word vector for each window. So this is exactly the way we defined it before, just with different notation. He has one hidden 10H layer, just like we did. And now, instead of having a softmax for finding, a named entity, he has a softmax over the entire vocabulary. So it has number of rows is the number of words in our vocabulary, and he just tries to predict the class being the next word. So I have A, and now tries to basically predict all the potential words that could come after I have A. And it tries to get a higher probability for all the things that a person can actually have. And in my case, it will train to predict cat. Of course, we'll never really assume that we could do a perfect job on language modeling, right? In some ways, you need a lot of world knowledge to do a perfect job at language modeling and really predict the correct word every time. You need to know all the context and all that. So in some ways, this is almost an AI complete kind of task if you wanted to do a perfect job. We have a long conversation, and then you're trying to predict every single new word before. Even for humans, that's hard. So basically, this part so far is standard, and here he basically then just adds these word vectors to again come into directly the final softmax tool, which is really just a sum here of the standard 2-layer neural network plus another gigantic matrix. Again, this has to have the number of rows be similar or equal to the number of words in the vocabulary, and so there's this bias term. And in the paper, he uses these equations, but really now you should be able to kind of quickly see through just, he calls what we try to sort of standardize and always call W for the first layer is W superscript 1, and for the second layer is W superscript 2. He just has, H and U and W here. So this is the original notation from the paper, and here he just, has the same softmax that we have defined before, and this is the picture. The problem with this is that we have a fixed window of context that we're only conditioning this on. And in some general way, of course, that could never work perfectly, right? If I only give you the last 5 or 6 words in order to predict the one that comes after that, you couldn't predict something where I say, I talk about Spain and the history of Spain, and then I say, and then the 2 parties or the 2 countries fought in the war off. And now, if you just have that sentence and you condition on it, then, the 2 enemies or whatever could fight in any kind of battle, like from the one today till, one before. But if you knew from previous context that it was about Spain, you could now maybe restrict to, give higher probabilities to cities or countries that are in or surrounding Spain. And this is one of the motivations for recurrent neural networks, which we won't be able to really fully go through in just 4 minutes, but I'll give you a little bit of a primer here. Basically, it is the solution that allows us to incorporate, in theory at least, arbitrarily large contexts to make a new prediction. And these predictions aren't just for the next word. Really, it could be anything. We could do named entity recognition, any kind of task where you try to predict something based on some previous language input. Recurrent neural networks can do quite well. And so we will have different kinds of notations, and if you read actual papers in the literature, you'll see different kinds of graphics to visualize models. So I want to introduce you here to three of them. The main idea of recurrent neural networks is that you basically use the same weights W here at every layer, and instead of sort of going up for one fixed input, you just go over time. Each new word will essentially get its own hidden layer. So these are our word vectors, just as we had before. Now they will feed in, and instead of having, for instance, 5 word vectors feed into your hidden vector, you actually have each at each time step only feed in one hidden one word vector into the hidden layer and the previous time step's hidden layer. So let's look at the math to disambiguate all these figures. Here are, again, two other kinds of figures that all visualize the same idea. Basically, this is the math that defines a recurrent neural network. And this is very important because you'll actually implement that in your next problem set. So we have, let's assume we have, with slight abuse of notation here, x being our word vectors. Now, all we do is at every time step t, we'll have a new input xt or x sub t. This is a different notation that we won't use as much, where we have the superscript here for time steps. In most cases, we'll stick to subscripts or x sub t. Now, the xt is here the word vector at time step t. So this is what we assign here with these square brackets, is the actual word vector that we again got from our word2vec implementation of problem set 1. And we basically multiply that by a matrix W here. And we sum that with another matrix multiplication here, where this is the hidden-to-hidden connections of the previous time step h. And for this, right now, we use a sigmoid. This is, again, a choice that we'll make, and there are actually other better choices than the sigmoid. And then at each time step t, we also have predicted output, which, again, is just going to be our softmax probability. And this will essentially define the probability here for seeing a specific word j. This could have also been, square brackets t at the next t plus 1 at the next time step. And just to wrap up the definition of a recurrent neural network in the last minute, basically here we can define the first hidden layer h0 before we see the first word just randomly. And we have basically the definition here of our hidden layer. We'll say the hidden layer has dh many units. And so our h hidden to hidden layer W matrix is a d by d matrix, and hx is a dh by d, where d is the dimensionality of our word vectors. And S is, again, in the case of language modeling, needs to predict for every single word a probability. So it's the size of our vocabulary times the hidden vector. And that essentially defines a recurrent neural network that will train with the exact same cross-entropy error that we had before, but now trying to predict words instead of named entity classes, and going one time step at a time. And how to really optimize those models and various tricks for really getting them to work, we'll cover in the next lecture.